Welcome, Dr. Tom Jenkins.
Thank you, Renee, and hello to everyone from South Carolina. I'd like to begin today's discussion by reviewing the 6 nutrient classes that we as nutritionists need to provide to all our animal population. And of course, arguably, water is often listed as the most critical of these since its absence would cause loss of function or death before the absence of any of the other classes. But I could also argue that lipid is the most misunderstood of these 6 classes for 2 reasons. First, the misconception that lipids only provide energy that could also be met by carbohydrate, and second, that all fat sources are equal and have no unique individual contributions. Later seminars will dispel both of these myths, but today's lecture is designed just to lay the foundation on the basic nomenclature and analysis to provide a good understanding for concurrent lectures. So we have 4 objectives that we hope to be able to accomplish today. We hope by this section is over, you will be able to define the difference between a simple and compound lipid and give a few examples of each. That you also be able to describe how feeds are analyzed for lipids, because we need to deal with lipid analysis in our feed reports all the time. And in the same regard, to be able to describe the difference between fatty acid content and fatty acid composition. And then finally, to describe the basic structure of fatty acids and how they are named. Now, there are many systems for classifying all the lipids that are found in animal feed, but I've chosen one that is basic, simple, and straightforward, and that is the lipids that are there are either based on glycerol or they're not. So the non-glycerol-based lipid fraction in the feed would include the waxes and alkanes that include the cuticle covering on plant surfaces. Now those are very important to the plant because they prevent water loss and the invasion of pathogens, but have little redeeming value to the animal because of their low digestibility and availability. So our focus instead is on the glycerol-based lipids, and we can subdivide those into simple and compound. Simple lipids contain only glycerol and fatty acids. Compound lipids the same, glycerol, fatty acids, but in addition what makes them unique is the presence of another nutrient group. So the anchor or the backbone to the lipids that are important to the animal are based on glycerol. The structure is shown here with its 3 carbon, and to each of the carbon is attached an hydroxyl group. And we can build the simple and compound lipids just by replacing one or more of the hydroxyl group with another lipid or carbon component. So let's take a look at an example of a simple lipid. Starting with the glycerol backbone, if we attach a fatty acid to one of these carbons, and I've arbitrarily just chosen the first one, and leave a hydroxyl on the remaining 2, then we've built the basic structure for the simple lipid that we call a monoglyceride. Now you won't find very many monoglycerides in the feed, but it is a very important lipid digestion product in the small intestine of the animal needed for fatty acid digestion and absorption. Now if we attach fatty acids, and I'll use abbreviation now, FA for fatty acids, and arbitrarily attach it to carbons 1 and 3, leaving hydroxyl in the middle, then we have the basic structure for the simple lipid called a diglyceride. And again, not very many lipids in this form in the feed, but it is a digestion intermediate in the digestive tract of the animal. And the final option is to have fatty acids attached to all 3 carbons in the glycerol backbone. And now we have a triglyceride lipid structure. And this one is important because it is the primary lipid form that's found in the cereal grains that we include in the diet. So all the oils that are extracted from the cereal grains, like corn oil or corn oil co-products like distiller's grain or soybeans, are going to exist with the lipid mostly in the triglyceride form. This is a form that you also find the lipids in animal fats if you use that in dairy rations, and that would include tallow and any of a number of different types of greases. So triglycerides are important in the feed. Now, moving from simple to compound, we start with a structure that looks like a diglyceride, glycerol and fatty acids attached to 2 carbons. But to make a compound, we need another nutrient on a 3rd carbon. And if we attach a mineral phosphorus there, then we have the backbone for the compound lipid class that we call phospholipid. Now, attached to the phosphorus can also be a wide variety of shorter carbon chain compounds. Now, a common one is the compound choline. It can be attached to the phosphorus to form the phospholipid that's referred to as phosphatidylcholine, or goes by the more common name lecithin. Now, example of one other compound, and there can be many others, but one other example is serine, which is actually amino acid derived from protein. So it's an example of how a lipid containing material can contain protein or amino acids. Now, another example of a compound lipid is if we have a sugar attached to the 3rd carbon. And then we've got the backbone structure for glycolipid. And this is important in the feed because it is the primary lipid fraction that are found in much of the plant matter of forages that we give to the animal. So while triglycerides are in the cereal grains and the oils extracted from the grains, glycolipid is oftentimes the primary lipid fraction that are found in the forages. Now, how do we analyze for these? Now, the analysis of lipids is based on the property that lipids are soluble in organic solvents and the other nutrient classes are not. So the procedures were built to wash the feed sample with organic solvents like ether to remove the lipid and then weigh how much was removed. So the picture on the left is the traditional apparatus that's used for ether extract analysis of feed in the old proximate analysis system that's still in use today. Now the one on the right, it reflects the more automated and semi-automated apparatus that are available today to assist with that process. But the question is, when you do an analysis by this lipid extraction, exactly what compounds are extracted? What are you calling lipid? Well, extraction in these solvents do remove lipids, but can also often remove the non-glycerol-based lipids that include the waxes and alkanes that we say have little value to the animal. Now, they will remove the glycerol-based simple and compound lipids, which is important. But in addition to that, remove non-lipid fractions as well. So if there's considerable amount of water remaining, it can be removed and counted as fat, along with fat-soluble vitamins and pigments. So there are a variety of non-lipid components that can swell up or inflate the lipid value that you have come back on your analysis sheet from the laboratory. Now, among all these lipids that are present in the feed, what's really important for animal health and production is the fatty acid portion that's found in the simple and compound lipids. This is a portion that provides a high energy, and we add fat to the feed to enhance the energy density, that's coming from fatty acids, not any of the other components. The fatty acids are the portion that can have tissue effects in the animal, such as improving reproductive performance, that will be talked about in later lectures. And the fatty acids are the portion that can have rumen effects, like the formation of bioactive lipids in the rumen that can cause milk fat depression. So many laboratories have gone to methods to isolate and just identify the fatty acid portion and give that along with ether extract values. So as an example, here are 3 common feed ingredients: alfalfa, corn grain, and corn silage. And these are values that are taken from CPM for dairy, and it shows the ether extract values for each, along with fatty acid values that were determined in the lab on an instrument called a gas chromatograph. And you can see invariably that the fatty acid content is considerably less than it is for the ether extract value, because the ether extract is inflated by the non-lipid compounds. So the fatty acid analysis provides us more pertinent information to be able to relate the lipid values we get from the laboratory to animal performance. Now, since fatty acids are central to all this and the most important aspect of lipids, we should know something about how they are named and the differences between them. Their structure is relatively simple. They are chains of carbons, and each of these links, carbon links in the chain, are held together by bonds. Now, the single lines that are shown here connecting all the carbon links are called single bonds. The fatty acid has an acid end that biochemists draw in this fashion, and it has a methyl end drawn in this fashion. And then there are different lengths of carbon in between connected by these bonds. Now, how do we distinguish between what could be hundreds of different fatty acids in the tissue of the animal and the milk? Even though the feed may contain 8 to 10 common ones, milk can contain hundreds of fatty acids. And we distinguish between them based on the length of the carbon chain, the number of double bonds, and the position of these bonds. So if it's a short chain, just 2 carbons to 5, we refer to them as short chain fatty acids. 6 to 12 carbons are referred to as medium chain fatty acids. And greater than 12, 14 to well over 20, are called long chain fatty acids. Now, number of double bonds is also important in identifying these. The example I showed in the previous slide had only single bonds, so there were no double bonds in the chain, and we refer to these as saturated fatty acids. A terminology that's already familiar to many of you, but we want to be able to review these so as we proceed through succeeding lectures, we'll understand the terminology that's used. One double bond in the chain is referred to as a monounsaturated fatty acid, and 2 or more double bonds is polyunsaturated. And these are often abbreviated PUFA. You might hear that abbreviation PUFA, referring to polyunsaturated fatty acids with 2 or more double bonds. And then the last way to distinguish different fatty acids from each other is the position of the double bonds. So the chain has a beginning and an end, an alpha and an omega. The alpha, or beginning of the chain, is next to the acid end that we described previously. The omega end is the methyl end. There are 2 systems for identifying double bond location. One is in reference to the acid end, counting in carbons in that direction. The other system starts on the omega end and counts in that direction. We're only going to concern ourselves with the omega system today because it's in wider use and more popular. So using the example at the bottom, this fatty acid structure, we can't possibly remember the names of hundreds of different fatty acids, so we have an abbreviation system that's in use. The abbreviation system is to write a C to refer to the number of carbons, and then the number of carbons in the chain, and if you count the carbons, there should be 18 of them there, followed by a colon, and then the number of double bonds in the chain. So you can see there's single at most locations, but there's 2 places where there are double bonds. So we write 2 after the colon to signify 18 carbons and 2 double bonds. And then we want to know the position of the first double bond from the omega end. We write omega or W and count in the number of carbons from the omega carbon until we hit the first double bond. 1, 2, 3, 4, 5, 6. So this is omega 6. This fatty acid is referred to as 18 carbon, 2 double bond omega 6 fatty acid. It has a name also, but it's too difficult to remember all the names. Now, with that abbreviation system in mind then, let's look at some common fatty acids that are in the feed of the animal. Now, this particular structure, if you count the carbons, you would see 16. So it's a C16 colon, no double bonds in the chain, 0 double bonds. So does that make it a saturated or unsaturated fatty acid? It makes it saturated because there are no double bonds holding any of the carbons together. The omega system does not apply because there's no double bonds. Now this common fatty acid found in the feed is worth remembering the name of. It's called palmitic acid. If you lengthen the chain by 2 carbons to a C18O, which is also saturated, this goes by the common name stearic acid. Now, the next one at the top, what would its abbreviation look like? It has 18 carbons in the chain. So 18 colon and 1 double bond just in the middle of the molecule. C18-1, it's an omega what? Count the number of carbons in from the omega end, 1, 2, 3, 4, 5, 6, 7, 8, 9, and it's an omega 9. Common fatty acid in the feed, it's called oleic acid. And if you wanted to boost up the oleic acid content of a dairy ration, what would be a good fat source to use? If you were thinking canola oil, you would be right. It's a very good source of oleic acid, or this 18-1 omega 9. Another example at the bottom, the one at the bottom is the most common unsaturated fatty acid that a cow consumes every day. Again, 18 carbons in the chain, but now we have 2 double bonds. C18-2, omega 1, 2, 3, 4, 5, 6. It's an omega 6 fatty acid and goes by the name linoleic acid. If you wanted to add an oil or a fat source high in linoleic acid, a good choice would be corn oil or soybean oil or distiller's grain, just to name a few choices. Cottonseed, sunflowers as well. All right, another one at the top, common in feed, important to the animal, 18 carbons in the chain, number of double bonds, 1, 2, 3. Omega what? You might have the answer before me by now. 1, 2, 3. It's omega 3. It goes by the name linoleic acid. And if you wanted to add fat sources high in linoleic acid, this omega 3, what would you consider? You would consider flax or linseed oil that comes from flax, or pasture. There's a lot of pasture species rich in this fatty acid grass. Now the last one I wanted to mention is shown at the bottom, a long complicated structure. And too long to write in all the carbons. It actually has 22 carbons in the chain. You can count the double bonds here, 1, 2, 3, 4, 5, 6. So it's a 22-6 omega what? This is a methyl end, 1 carbon, 2, 3, it's omega-3. It has a long name, but we're just going to refer to it as its abbreviation DHA. And where would it come from? And most of you already have that answer. Fish, oil, or fish products would be a good source of this fatty acid. So those are all ones that will come up frequently in later lecture series and are worth remembering. So here's a breakdown of some common feeds that we use in dairy rations showing fatty acid content. What is the fatty acid as a percent of the dry matter in that feed? Alfalfa, 1.4% on a dry matter basis is fatty acids. Corn, 3.2. This is the fatty acid composition, the relative proportions of the individual fatty acids. So alfalfa is lower in fatty acid content and lower in linoleic acid, the 18.2, but higher in linoleic acid, the 18.3. So with that in mind, here are a few key points. First of all, I wanted to emphasize that fatty acids are indeed the most important lipid fraction in feeds that will gauge how our animals respond in animal health and production. Most of the feed fat analysis that we're dealing with will include fatty acids plus other non-lipid fractions. That's a traditional ether extract that we get back as a lipid value and oftentimes does not isolate the fatty acid value. Some you can request in many labs now a fatty acid analysis to go along with that. Both fatty acid content and fatty acid composition are important and will be part of your feed analysis oftentimes, and there are wide differences in types of fatty acids and their sources, and that will have an impact on animal health and production. So with these points in mind, I want to thank you, and I want to turn back over to Renee, our moderator. Thank you.
Thank you, Dr. Jenkins. That was a great review and refresher for all of us. It looks like we've got a couple questions that have come in, but I also wanted to just remind everyone if they do have specific questions that came up as you were listening to Dr. Jenkins speak, please feel free to enter those in that question box that's in the lower right-hand panel, and there's a little button to hit send, and then he'll be able to see those questions and answer them as well. And we'll try to keep this question answer session to just 10 minutes, and then any questions that we don't get answered live, we'll be sure to send those out to all of you via email so that all of your questions are addressed. With that, Dr. Jenkins, if you want to answer some of those questions that have come in.
Yeah, I see one that came in. It's a very good one, and I'm glad somebody brought it up and thought about it. It's asking, is it important to have a certain type and amount of omega fatty acid in the diet? Now that we've defined omega fatty acids, they're asking, what is their importance when it comes to their content in the feed? Well, we talked about 3 classes of omega fatty acids in the diet: omega-3, omega-6, and omega-9. Now, the omega-3 fatty acids, I'll get back to my pen here. The omega-3 fatty acids we mentioned included oleic acid. Very important fatty acids that the tissues need, but the tissues are capable of synthesizing it, and we think synthesizing all that they need, so it's not critical or essential that you have that one in the diet. But the omega-6, which was linoleic acid, I'm sorry, somebody probably caught that mistake. Oleic acid is omega-9. The omega-6 fatty acid is linoleic acid, and the omega-3 we said was linoleic acid. And there's different omega-3 and omega-6 products that are critical for the proper tissue function in the animal, but they all are derived from these 2 parent compounds. These are called essential fatty acids, and it is important to have enough of these being digested and absorbed every day to meet the needs of the animal. Later on, when we get into the repro lectures, there is evidence that we don't always have enough of them. Now, the cow eats plenty enough of these every day, but the problem is that the microorganisms in the rumen can destroy them and perhaps limiting the supply to the tissues of the animal. So the omega-3 and the omega-6, we do need to worry about having those in the diet and supplying them to the animal each day. Another one that just came in was, the question was, are the fatty acid contributions from forages and grains so small compared to the fat supplements that they can be ignored? Well, the fatty acid content certainly is much higher in the fat supplements, no question about that. On the slide I showed you, it was 17 to 19% fatty acid content in cottonseeds compared to just a few percent in corn silage and corn. But we feed relatively small amounts of fat supplements compared to these forages and grains. For example, it might take 12 to 15 pounds of corn grain, and you would come up with the same amount of lipid being supplied to the animal as 3 to 4 pounds of cottonseed. Okay. So it's just the sheer volume of the forages and the grains, even though their fatty acid contents are lower, that can provide a healthy supply of lipid coming in through the diet every day. So we need to consider fatty acid contributions from all sources, especially the unsaturated fatty acids. And later on, I'll be introducing and talking about a concept that I refer to as RUFL, which is rumen unsaturated fatty acid load, that accounts for all the major unsaturated fatty acids that are consumed, 18.1, 18.2, and 18.3 from all sources in the diet, as a help to assist us to be sure that nothing gets left out when we're trying to diagnose fatty acid related issues in the diet.
Dr. Jenkins?
Yes.
Looks like there's a couple of other questions that came in, and if I can share those with you and we can address well. The first one is, how different are the results on forages and main commodities from lab and book values?
Okay, very good, excellent. The lab values versus the book values, they're the same as what you would expect for forages. Right? Many different factors can affect the fiber content and the digestibility and degradability of the fiber fractions that are present in our forages, and the same can be said for the lipids as well. So there can be considerable variation in both the fatty acid content, less in fatty acid composition. So let me use corn silage as an example. That's corn oil. Corn silage is basically corn oil. Now the fatty acid composition is going to be relatively always the same, but the fatty acid content can vary considerably. And I've seen fatty acid contents in corn silage that were double or more from the lowest to the highest, and that can have a big impact on the amount of lipid being consumed by the animal and be a big factor in trying to diagnose problems such as milk fat depression. Book values are not going to reflect those differences in corn silage that may occur depending on the environment, the region of the country, stage of harvesting, and things of that sort. So it could be important to, as it is for fiber, to get those analyzed.
Dr. Jenkins, there's one more question that we have, and that's probably about all we have time for. And this one looks like it's somewhat related to that same topic on the differences in book values. This question is, most of the database ingredient analysis report crude fat. How can we now compare these new fatty acid values?
Yes, yes. Well, the best thing you're going to have to do from here forward is get the feeds analyzed for fatty acids. Those services are available now, and the costs are very competitive. And I don't think the costs are going to be prohibitive in us asking for fatty acid analysis. Now, I think there's some hope that we could just do the traditional crude fat or ether extract value that you have in your reports now, or that we have in the books, and we could somehow estimate a fatty acid value. Now, there were some thinking that you could estimate fatty acids by taking the ether extract -1. And if you look at the table that I gave you for ether extract and fatty acid values for those 3 feed ingredients earlier, 2 out of the 3 this worked very well. The third one it didn't. So it's just not very reliable to depend on this estimate. There's no good predictable relationship that allows you to accurately estimate fatty acids from ether extract. So the best advice is to request and ask for fatty acid contents from your lab, along with, and usually you'll get at the same time the crude fat or the ether extract values.
Great. Thank you, Dr. Jenkins. I think it's time for us to wrap up, and I appreciate all the work that you've put into this presentation and sharing this information with us.
Thank you, and I especially want to thank the participants who took time out of their schedule today. I enjoyed the opportunity to share some thoughts with them, and I want to thank Bertus as well for the opportunity to be a part of this first of many exciting series coming along here. Thank you.